Hello everyone and welcome back to L582, Modeling and Control of Electric Machines on Drives. In the past lecture we started talking about the single-phase induction motor, and we said that is one we call special machines because they are not that very much popular like the synchronous and the three-phase induction machines, but they're still popular enough to be dealt with. The single-phase induction motor is very popular as being just needed a single phase source, which you can find in everywhere. Okay, so it's just some sort of a plug and play motor that you can just plug it to your outlet and it will work. So it's very popular for the domestic and the small applications. You can find it for small facilities. Okay, like we said, the construction of this motor just like the three-phase induction motor. So the stator core, just like the same stator core, just have an iron core with slots inside it which holds the winding, and the rotor is a square cage type, so you have also slots, and you have aluminum or copper bars inside those slots and just shorted together with end rings, just like square cage induction motor. But the main difference is it just have a single phase winding like you see here. So it's a single winding fit from a single phase supply. So like we said, for the three-phase winding fed from balanced three-phase supply, you will have a rotating magnetic field, while for the single-phase winding fed from a single-phase supply, you'll have a pulsating magnetic field. That means the poles will be just stationary, fixed in position, but they will keep changing magnitude and polarity. But they are not rotating, and that's why it cannot create torque on its own. That's why the starting torque of this motor will be zero unless we find some way to make it not zero by starting it. And we just brought this down the mathematical representation that this pulsating MMF can be represented mathematically like the summation of two rotating MMFs, but they are in opposite direction. So while you just have this one winding, those two MMFs will be equal in magnitude and opposite in direction, so the resultant will be zero, and that's why the pulsating MMF does not go anywhere, does not rotate. Okay, and the machine will not create torque unless we find something to make one of those two MMFs, rotating MMF, higher than the other. We call them the forward MMF and the backward MMF, and our mission all the time is to reduce the backward MMF and make the forward higher. Then you get a resultant MMF and the machine start developing torque and start rotating. Okay, so I started talking last time about the starting of single phase induction motor and how we can start this. So the main idea is using another winding, not just our single phase winding, main winding, but use another one on the stator also. We call it auxiliary winding. So we have now two winding, and by making them perpendicular in space 90 degrees, now we have balanced two-phase winding, because we said that this idea of having a balanced three-phase winding fit from a balanced three-phase supply will produce a rotating magnetic field is not just exclusive for three-phase systems. Okay, it just can be done for any number of phases you will do. You just make sure they are balanced. Okay, so you can use 5 phases as long as they have balance. Okay, so the angle is just 360 divided by 5, and now you just make sure they're just sharing this circumference of the stator equally, and those will be balanced. And if you have a 5-phase supply feeding them, now you will have a balanced 5-phase system, and you will produce a rotating magnetic field. So it's not, like I said, it's not exclusive for 3-phase winding, so we can do it with just 2 phases. So we'll use another winding, the auxiliary winding, and the others will share the circumference like you see in here. So they are perpendicular in space, 90 degrees apart, so they are just like that. They are balanced. If you can have their currents, the electric currents moving inside them, to be also perpendicular, that means they have 90 degrees phase shift between the currents in the main winding and the auxiliary winding. Now you're good to go. Now you have balanced currents feeding balanced windings, and now you're creating a rotating magnetic field, and that means you are just cancelling the backward magnetomotive force, and you will have just the forward one, and it is rotating magnetic field just like the 3-phase winding. But like we said, we cannot feed to those windings with 2 different supplies, because like we said, we will not sacrifice the advantage of this motor, which is just being fed from a single phase supply, which we can find it in any outlet in your home or any other facility. So it's out of space just here to think we have two different voltage sources with 90-degree phase shift between them and feed the main winding and auxiliary winding from different sources. That will not happen. So we need to just work out and have different tricks to just use one voltage source, and yet from this one voltage source we create two currents with just 90 degrees phase shift between them as much as we can. Actually, if you just reach this 90-degree phase shift, you will just cancel the backward MMF entirely. But if you just have any kind of phase shift between them, it will not cancel the backward MMF, but the forward will be higher than the backward. You're just weakening the backward MMF, and the machine will start to develop torque. Yeah, it's not that much, but at least it will start. Okay. So the first one we talked about last time is the split phase motor, and that's how it is. It just you have the main winding and auxiliary winding on the stator and connect them in parallel to the one phase or a single phase supply, the same one. The whole point is we play with the design of those windings and make the auxiliary winding wires we use for just wiring the coils of the auxiliary winding, make it thinner, and this will make its impedance different from the impedance of the main winding. So when you just find the current and the auxiliary winding, which is the voltage divided by the impedance of the auxiliary winding, will have a different phase angle compared to the main current, and this different, like we said, will just weakening the backward MMF and keeping the forward MMF just having its value, so the resultant will have some torque. Like we said, this theta is not 90 degree. The phase shift between the two currents is not 90 degree because it's just some difference and the impedance will not do the job for you. But like we said, we just try to weakening the backward MMF a little bit, so we just create some resultant MMF by just summing those together, and this will create you starting torque. It's not that much, but the motor will start. So like we said, if you look at the torque speed characteristics here, the red one is just using the main winding only. Like I said, the starting torque is 0. And the black one is using the main and auxiliary winding together here, and you will have a little bit of starting torque. It's not that high, but it will be good enough if your load is not that high. So you're using this kind of a motor just with not big loads, especially at the beginning, because you will not be able to start a very heavy load. But if your load is not that heavy, a small fan or something, that just could do the job. Okay? The whole point is make sure you look at here, because the auxiliary winding is thinner wires. They will not handle to have the high current going all the time. So we use this switch here, the mechanical switch, just to this mechanical switch here, which senses that the speed of the motor reaches the steady state speed. That means you passed already the starting period, and now it opens to get the auxiliary winding out of the circuit, otherwise it will heat up. Okay, and the motor will keep running just with the main winding, and that means your backward MMF has just back to be high, but you'll now, once the motor already started, the inertia of your moving parts will just push the forward MMF to be higher than the backward MMF, and the motor will keep rotating. Yeah, again, it's not that good performance because you will have this backward MMF which works as a brake all the time, but like we said, if you're having just a small load, it's not that a big of a deal, then it's good enough. Okay, guys? Like we said, it's not the best option to go with unless we have a very small load, very light one. So once we go higher, we go with other means. So the second method you use here, we call it Capacitor Start motor. Okay, what is this? So let me grab you again the schematic diagram of this guy. Okay, it should be this one. No, sorry. Okay, so this is coming from here, so yeah, this one. Okay, that is the schematic diagram of the capacitor start circuit or motor. Okay, like we said before, here is our single phase supply, that is the V supply, and as you see, that is the current going to the auxiliary winding and the current going to the main winding. This is your main winding and this is your auxiliary winding. The total big difference here is you have a capacitor here. Okay, still there is a mechanical switch just doing the same job like before. When you just pass, this just opens after speed reaches steady state. That means you just use this capacitor along with the auxiliary winding for starting, and after starting you just get rid of them, okay, and keep going with just the main winding. But what this capacitor doing here, it's doing all the job if you're thinking of this. Okay, the whole point is using capacitor in series with the auxiliary winding gives 90 degrees phase shift to its current. You know that from your circuits courses. It's just the capacitor all of the time gives you a 90-degree phase shift. Okay, so you just leave the auxiliary winding as it is, but actually use the capacitor with it, and now you just make sure now the phase shift is 90 degrees. So using the capacitor, now the I main, the current in the main winding, and I auxiliary will have 90-degree phase shift at starting, and that's what we need actually. Okay, because this cancels the MMF, let me call it F capital, backward. And if you remember, the total F of the pulsating one, or we'll call it the total one, is the F forward minus the F backward. And using the capacitor, you have just make the F backward equal 0. And that means you just taken out this braking force we're talking about, and now your MMF is just forward one. Like, remember, here is your F forward, and there is here F backward. Okay, like we call this the brake. It's just acting like a brake. So if you manage to do this, you basically canceling this out, and the total will be the F forward, and it's just rotating like the one you can find in a three-phase induction motor, and the machine will start with a higher starting torque. Okay, so this get rid of F backward, which significantly increases the starting torque. Okay, guys? So we trying here to look at, again, the torque speed characteristics of such a motor. Okay, it will look like this one. Okay, that is the torque speed characteristics of the capacitor start motor. Like you see in here, just if you compare this one to the one with the first method, which is just the split phase motor, you'll have much higher starting torque here. We start on the black curve, which is the starting one here, and the motor starts from here. It just have much higher starting torque. Look back here to the torque speed characteristics of this one. The black one, seeing the starting torque there, it's very small. Okay, but here, by canceling the backward MMF, now you have much higher starting torque here. And the motor will keep going on to this characteristics until the switch just opens and get out the capacitor and the auxiliary winding out of the circuit at all, and you just jump down to work on the main winding one. So like we said, this red one is just using main winding only, while the black one using all of them, main winding plus auxiliary winding plus capacitor. Okay, so this gives you much higher starting torque, while the starting torque without using this, just the main winding, is 0, like we said before, because you just have the pulsating magnetic field and just the main winding, so it's not rotating anyway, because the forward and the backward MMFs are just equal, so they will cancel out and you will not have any torque produced. But with having the auxiliary winding and the capacitor, you're now having balanced two-phase winding fit from balanced two-phase currents, because you have 90-degree phase difference between the two winding, and that's it. That means you will have just a rotating magnetic field, and this will give you a significantly higher starting torque like you've seen here. And after this, you just go back to the running ones here after the switch opens. Okay, guys? Okay. So again, what about the pros and cons here for this method? Okay. So the pros here, just obvious that higher starting torque. Okay. And that's good. Well, what about the cons here? Just to keep in mind that additional capacitor means more cost. Okay, so it's more expensive because you just need to add a capacitor to all of that. Okay, but just apart from the cost, there's another thing. It is just still the auxiliary winding and capacitor are disconnected after starting. Okay, and this will make the F backward goes high again, acting as a brake, reducing torque and giving poor running performance. So actually this motor is good for starting, but it's bad for running. Okay, because again you're just disconnecting the auxiliary winding and the capacitor from the motor after the starting period passes, and you're just going back to just using the main winding. So we back to the same problem. Is just the backward MMF is just grown big again, and it's just the only thing that's making the forward magnetomotive force higher than it is just the inertia of the moving parts of the motor, and this is not that much. So the motor is not that high in torque while running. Okay, so this method is good for applications require high starting torque and not concerned about running torque. Okay, yeah, there's some application like that, especially for the high inertia applications. You just need to move a heavy mechanical load from standstill, but just have a zero speed, so it has high inertia, so you need high starting torque to just make it run, and after it runs it does not require that much torque to keep it running, you know. So for this kind of application, yeah, that's good to go with this capacitor start one, because it will give you high starting torque at the beginning, and that's good for you just to overcome this inertia and make the load start rotating. But after this, you're not concerned about having high torque anymore because your load does not require that much of a torque to keep it running after it already have just pushed. Okay, guys? So that's the second thing. Like you're saying, you're just having a capacitor now with the auxiliary winding. Okay? Okay. The other just coming one is now, yeah, those stuff here just will be much easier because we now understand the basic principle. So the third one is call it the permanent split capacitor motor. Okay, most of the time we call it just capacitor run motor, and it just should be very easy to understand from its name now. Should be the same thing, but it will not go anywhere. Okay, so I'm gonna give you again photo for the schematic of this motor. That is our schematic again. Did the same thing like the other one, but you do not have a switch here, so no switch. I'm sorry. Okay, that means, yeah, it does not go anywhere. Okay, so this thing is the same like the capacitor start one, but no mechanical switch is used to get rid of the auxiliary winding and capacitor after starting. Okay, so that should be good. So the whole point is we'll not get rid of anything. The motor will keep running with this schematic all the time. We'll not getting rid of thing and just keeping the main winding alone. No, the main winding will not be alone in any way. It will keep working all the time with the auxiliary winding and the capacitor. Okay, for the starting and the running conditions alike. So you just keep using this all of the time. Okay, so if you want to look at the torque speed characteristics of this kind of a motor, it will look like just this one. Okay, that is the torque speed characteristics of this motor. Like you've seen here, you don't have two characteristics, black one or red one, one for the running, one for the starting, because the motor does not change configuration. It is the same thing all the time. While starting or running, it is the same configuration. We're not disconnecting anything. The motor just works the same. Okay, and that's why we call it just run, because they are all the time the same. The whole point to look at is, okay, here you have starting torque, yeah, but it's not that high. The starting torque here just comes again because you have an auxiliary winding and a capacitor and all that stuff, and that will just should be canceling out the backward magnetic motive force and give you a high starting torque. But if you look at this amount of starting torque here, is not that high like the one with the capacitor start one. Look here, this one is very high, a very high capacitor starting torque, but if you look at it here, it's not that high. Okay, why this? So let me explain this for you. The whole point is, in order to get exactly 90 degrees phase shift, the capacitance of the utilized capacitor has to be chosen according to the other impedances of the main and auxiliary windings. Okay, so it should be easy now. If you wanna just design this, if you wanna choose the amount of capacitance, because we didn't know how much capacitance we need, we use a capacitor, but not any capacitor will do the job. You'll have to figure out the capacitance of the capacitor you wanna just use to do this. And to do this, you have to know the impedances of the main and auxiliary winding that is already there, and then you make your calculations and find out the capacitance that will make the phase difference of the two currents will be exactly 90 degrees, because that's what you want. Okay, and that should be good. Okay, we can do this. We can just find out the main and auxiliary winding impedances and that's it. But it's not that easy. Why? The problem is the phase angle of the motor current changes with speed. Okay, because the slip changes. It's still an induction machine, guys. Yeah, and with an induction machine, if you change the speed, the slip changes with it, and the value R2 over S in the equivalent circuit of the machine changes. So this changing the impedance, it's the same like what we did with three-phase induction motor before. If you remember, the different speeds give you different slips, and the different slips give you different impedances in the machine. That's why, if you remember, why the starting torque with three-phase induction motor was so high, because actually the impedance of the machine at starting is very small, because the slip is just 1. But with the increase in the speed, the slips goes lower and lower, and this gives you higher and higher impedances. So the same thing here, because it's still an induction machine and still there is a slip. Okay, so the whole point is, the problem is the phase angle of the motor's current changes with the speed because the impedance changes with slip. Okay, so to keep the phase angle theta equals 90 degrees all the time, the capacitance of the capacitor has to change with speed, and this inapplicable. Okay, we cannot do this. You cannot have a capacitor that you can change the capacitance with this easy thing. All we can do is just we use different capacitors banks and just switch them on and off, and that's a very big headache. We'll not go through it. So we just have one capacitance and that's it. So the whole point is, and the whole problem is, for this method, okay, the capacitor run method, okay, the capacitance is chosen to give theta equals 90 degrees at rated speed, not at starting. Okay, so this method gives high running torque but lower starting torque, because like we said, we cannot choose the capacitance to be good at starting and good at running at the same time, because they're different. the motor at starting has different impedance compared to the motor without running. So we cannot change a capacitor that gives us both good starting and good running conditions. You know what I mean? So this method gives a high running torque, okay, but lower starting torque, because at starting the chosen capacitor value is not correct to cancel out the F backward entirely, but it weakens it. Okay, so you will not getting rid of the backward magnetomotive force at starting entirely, but you will weaken it a bit, and this will give you some starting torque. Okay, but it's not that high as the one. So because it's just good for this, we must have higher running torque. So you should be knowing what's happening now. This method is good if the application requires high running torque but not much starting torque. So this method is the opposite compared to the previous method. So the previous method is good for starting. So the capacitor start motor, we designed this capacitor to just be good at starting and completely cancels the backward MMF at starting, and this the motor starts with a very high starting torque, and just after the starting period goes, you just open the switch and get rid of all the auxiliary winding capacitor, and that's good because you're not concerned about the running behavior of the motor. You just need to make a high starting torque motor, and that's it. The other method is just if you want the running torque to be high, but you're not that concerned about the starting torque. Still, the motor has some starting torque, so it will start, but it will not have that much higher starting torque. But it will have good running torque, running performance. It will give you high torque at the rated speed, which should be the speed where the motor will keep running at. Okay? So we're designing this capacitor for this case to just cancel out the backward MMF at the rated speed, not at starting. So at starting, there will be some backward MMF, and that will just reduce your starting torque a bit, but you will have a good torque while running. So all the time I'm saying, the application guides you. Whatever the application you want to go with, it will just give you the idea which kind of a motor you have to pick, because as I was saying, you cannot just take advantage of everything. All the time, if you want to win something, you have to just lose something. It's how the life works, and especially how the engineering application goes. Okay, guys? Okay, so now we have two methods. One of them gives you good starting performance but poor running performance, and the other one gives you good running performance and a poor starting performance. So the fourth one should be obvious that we will go with both of them at the same time. Now we have the fourth method, which is the capacitor start, capacitor run method. Okay. So for this, your schematic will look like that. Okay. It is this one. Okay. So yeah, it should be just good for now to understand what's happening. Now we're just mixing the two methods together, the capacitor run and the capacitor start methods together. That is your V supply. and that is the main winding, that's your auxiliary winding. And now you have C-run, that's a capacitor here without a switch, there is no switch here, but another capacitor here with a switch. Okay, so should be understanding what's happening now is just this method combines the previous two methods. Okay, you have an auxiliary winding and a capacitor that is designed for running condition. Okay, so this combination gives high torque at the rated speed. Okay, in addition, we use another capacitor designed for starting condition, giving high starting torque, and after starting period passes, the switch opens to disconnect this starting capacitor leaving the machine to work with the main auxiliary windings and the capacitor and the running capacitor. Okay, guys, like this. So this method gives both good starting and running behaviors. Okay, so it is good for almost any application. Okay, but really expensive. Okay, now we're talking about two capacitors, auxiliary winding, and a switch. All of those actually costs money. Okay, that's just to keep in mind. Okay, so again, lots of saying, you'll win something and you'll lose something. That is the whole point. So yeah, we can just go with this complicated one. Now we have an auxiliary winding and a capacitor run, and they will keep attached to the main winding all the time, but using another capacitor just for the starting behavior and use a switch for it exclusively. And this switch opens after the starting period goes, and this will get rid of the starting capacitor and keeps the machine running with the main winding, auxiliary winding, and the running capacitor. Okay, guys? All right. So if we look at the torque speed characteristics of this motor, it will look like that one. Okay, yeah, this one, sorry. That is the torque speed characteristics of the capacitor start, capacitor run motor. Okay, you can see what we are talking about here. Now we having both high starting torque, because you're using a dedicated capacitor for this, and the machine keeps working on this torque speed characteristics until the switch is opened, and when the switch is open, just the capacitor goes away and the motor can work on this one, on the running characteristics, and this will give you both high torques. So for the running condition, you have the main winding plus the auxiliary winding plus capacitor run. Okay, for the starting, you will have main winding plus auxiliary winding plus running and starting capacitors. Okay, guys, that'll give you both good starting behavior and good running behavior, but it all comes with a cost. Okay, guys, so the whole thing, I cannot just give you an advice which one of those methods you should go with. Again, like I'm saying all the time, everything comes with the pros and cons. So for this method, you just use it if your application requires high torque all the time at starting and at running, because you will just pay money for this. If you have just an application that requires high starting torque but not concerned about how much torque with running, then you go with the capacitor start. If your application requires high running torque but does not require that much of a high starting torque, then you go with the capacitor run method. If you have just a very small light load, you don't need to bother with all this. You just go with this permanent split or just a split phase motor. At the beginning one, you don't use capacitors at all. Okay, guys, so it all depends. From other perspective, to keep that in mind, because that's important here, that this method only one, the capacitor run motor, okay, this one requires no mechanical switch, which is good for less maintenance. Okay, because this mechanical switch is some sort, where we call it a mechanical switch, is after all a switch. The whole thing is this mostly works like a centrifugal force switch. Okay, so this switch we are using with all those different methods, apart from this one, the capacitor run motor or the permanent split capacitor motor, while you don't need to just get out anything out of the circuit. But for all the three other methods, we use this switch, this mechanical switch. Okay, so the mechanical switch we are using, I'm gonna just talk about it a little bit. Yeah, so the mechanical switch we're using here okay, is just designed to sense the centrifugal force on its moving parts, and after it gets high enough and gets high enough with speed high enough, it opens. Okay, so it's how this actually switch works. It's just a mechanical switch that's attached to the shaft of the motor, and this is just designed to work with this. It just runs with the shaft as the speed goes up and up, and just since the centrifugal force acts on it, this force goes higher with the higher speeds. Okay, So it's just designed to send some speed, and after this it just automatically opens and it will open this. Okay, the whole point, as like we're saying all the time, mechanical systems fails a lot and requires frequent maintenance and an inspection, and this is not preferable. So that I'm saying, if you can go with this method, with the capacitor run method, you should definitely go with it, because you will get rid of the headache of this mechanical switch. Okay, it requires maintenance a lot and inspection a lot because of all this mechanical headache inside it. So that's what I'm saying. If it does not require high starting torque, then you should go with this method most of the time, because you just will get rid of all the headache that comes with the mechanical switch. Okay, guys? Also, this mechanical switch is fairly expensive. Okay, and also it is expensive. So we don't like to go with it. It's expensive to buy and to actually install inside the motor, and it also requires frequent maintenance and all that stuff. So we try to avoid it as much as we can. But yeah, and many times we cannot just avoid it because we need high starting torque. And whenever you need high starting torque, you even go with the capacitor start one or the capacitor start capacitor run one if you need both high starting and running torque. But if you're just good with having a decent amount of starting torque at the beginning and a good torque with the running, then you definitely need to go with the permanent split capacitor motor, or what you call the capacitor run motor, where you get rid of the mechanical switch and does not bother around with mechanical parts that needs to be frequently maintained to keep working its job efficiently. Okay, guys? So those are 4 methods to just try to start the single phase induction motor, and it will just work good enough. Okay, you can find this motor around all the time, and it is very actually it's unique for using the capacitor. So most of the time you will be dealing sometimes with home appliances, and you have a technician comes out to fix something. He will say most of the time that the capacitor needs to be replaced. Then it should ring a bell in your head that he's talking mostly about a single phase induction motor, and that's because most of the time the thing that's just blows up and needs to be replaced in the system be the capacitor. So if you have a single phase induction motor system and it just stops working, most of the time look at the capacitor, because most of the time the capacitor needs to be replaced, and that will fix your problem. Okay, it's just because the capacitor, most of the capacitor just fails a lot compared to other stuff. So that's the whole thing to just keep in mind here. That should be good with all the information I need you to get out about single phase induction motor. As always, there's so much details upon this, but it's not the place for it in this course anymore, because we're trying just to give you an overview about those kind of special machines. You can again refer back to your recommended textbooks if you want a so much in-depth discussion about single phase induction motors, but I'm very good about this overview now. You should understand what's happening and how this motor works, and about the modeling stuff and the equations and all that stuff. If you really need it for your work or something, you can just easily find it in any machine's textbook that's dealing with this, and you will not find much problem to understand it, because it's very much similar to the 3-phase induction motor with the minor changes. Okay, thanks so much guys for joining me today. There will be still one lecture list, and we discussing it again, an overview about these tipper motors and switch reluctance motors, to again give you a good idea about those kind of machines and how you can find them. Okay, thanks so much guys for joining me today, and I hope to see you all next time.